Hi there, this is some moments exam questions. This is part two. So I've done the first part of 2 questions on, and this one has 2 questions. The questions are of, exam standard, and they're quite challenging. So let's look at this first one. If you want to pause and have a go at this as it is, then that's great. And then when you're ready to move on, have a look at the answers. Just obviously play the video. So the counterweight, so basically we've got this set up in the image, and it says the counterweight, which is on the right hand side, is of uniform material and has a weight of 50 newtons. And it is 0.6 meters long. Okay. Then the next bit says water has a density of 1,000 kilograms per cubic meter. The bucket, which is on the left hand side, also has a mass of 15 kilograms itself and a capacity of 0.2 cubic meters. And the question says, when the bucket is full, calculate the force required by the operator to keep the system in equilibrium. So what we're looking for essentially is the force that this operator needs to push down with F to keep the system stable. So the first part is the counterweight is a uniform material of weight 50 newtons, and it's 0.6 meters long. So that means that the 50 newton weight of this object will act from the center. So the 50 newton force from the pivot will be, we've got to look at these distances, and it's the 3.2 minus half of the 0.6 because it acts in the middle. So we've got to subtract 0.3 from 3.2. So the distance to the center of the counterweight is actually, let's put this line in, is actually 3.2 minus 0.3, which is 2.9 meters. That's a really important part of this question. The second part of this question that's really important is that we need to find the weight of this bucket. So there's a couple of things here. We've got, we've got this amount of water. So we've got 0.2 cubic meters of water, which is quite a lot. So basically mass is equal to density times volume. So the density is 1,000 kilograms per cubic meter multiplied by 0.2 cubic meters. So that gives us, a mass of, there's 200 kilograms of water in that bucket. And then we've got to add the 15 kilograms of the bucket. So obviously 200 plus 15 gives us a total mass on the left-hand side of 215 kilograms. And what we need to do, because this is a moment question, is to convert that into a force. So we need to do, weight. The weight of the object is mass times gravitational field strength. So we need to multiply the mass by the gravitational field strength of 9.81, which gives us a total weight of 2,109.15 newtons. So add that to the diagram, 2,109.15 newtons. So basically we've got everything that we need now to find the force required by the operator. So what we're going to do is to sketch this. So what we can say is that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. And then I'm going to take moments from the pivot. The reason I'm taking moments from the pivot is because it's number one in the center. And number two, there's a normal reaction force that's actually acting upwards, and I've got no idea what that is. So we're going to take moments from there, so we don't need to know what that is. So let's deal with clockwise first. So we've got the counterweight itself, which is, so force times distance. So we've got 50 newtons multiplied by the distance, which we said was 2.9 meters. So we'll deal with that in a second. Plus the other clockwise moment is the force from the operator multiplied by the distance, which would be the full 3.2 meters. So that's clockwise. We've got to make that equal to the anti-clockwise. Now the anti-clockwise is the bucket itself. So that would be 2,109.15 multiplied by the distance from the pivot, which is 1.4 meters. So if you put all that in your calculator, what we'll end up with is the 50 times 2.9 is 145 newton meters, plus we've got 3.2 lots of F equals the 2,109.15 times 1.4 is 2,952.81 newton meters. Then we need to get rid of the 145, so we're going to take that to the right hand side and subtract it. So we end up with 3.2 F equals, we've got 2,952.81, subtract 145. Which is, you should have got 2807.81. So the force required by the operator is simply 2,807.81 divided by 3.2, which gives us 877 newtons. If you got that, really well done. That's quite a tricky question. So let's have a look at the next one. Now the next one's actually written wrong. I'm going to change it slightly. So on this one it says uniform meter ruler AB of weight 0.5 newtons has a 0.5 newton weight placed on the 20 centimeter mark. What I'm going to do is to change one of these. So let's change that to 1 newton. So if you want to have a go at that now, that's great. And then I'll take you through the walkthrough solutions in a moment. Okay, so turn that back blue. We've got a uniform meter ruler AB of weight 1 newton, has a 0.5 newton weight placed at the 20 centimeter mark. Calculate where the pivot would need to be moved to in order to balance the ruler. So it's not a very straightforward one, it's quite a tricky one. So there's the ruler, I'm going to call that AB. And the pivot would actually be moved from its central position somewhere left. And what we need to do is calculate where it would need to be moved. So you should have calculated either how far it needs to be moved from its central position or its new position on the ruler itself. So from the center of its original position, I'm going to call that distance X. And then the ruler itself from the center has a weight of 1 newton. So let's sketch that in. So we've got a weight of 1 newton. And at the 20 centimeter mark, we've got a 0.5 newton weight. So at the 20 centimeter mark somewhere there, we've got a 0.5 newton weight. Now what we need to do here is we're going to take moments from the new position of the pivot, which is the new balancing point. So we've already established that the distance from the original position to the new position is X. What we need to do is realize that the original position was at the 50 centimeter mark of the ruler, and the 0.5 newton weight is actually at the 20 centimeter mark, so I could call that 0.2. We're going to move at a distance X. What we need is this distance. Okay. Now that distance is simply the full difference. So the difference between 0.5 meters and 0.2 meters, which is 0.3 meters, subtract X. So that there is called 0.3 minus X. Obviously, the full distance is 0.3 and we are subtracting X. So hence the 0.3 minus X. Then what we need to do is take moments from the new pivot point, which we're going to do now. So same as always, for this type of question, we're going to say the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. And we're going to do clockwise first from the new position. So we've got 1 newton times distance X. So 1 times X is obviously X. Equals anti-clockwise, we've got the 0.5 newton force multiplied by the distance, and the distance from the new position is 0.3 minus X. So we've got X on the left hand side equals, so we've got 0.5 times 0.3, which is half of 0.3, which is 0.15, minus 0.5 lots of X. Then what we need to do is take the 0.5x from the right hand side to the left hand side, which will be plus a half X. So we've got X plus a half X, which is obviously 1 plus a half is 1.5x equals 0.15. So X would be 0.15 divided by 1.5, which would give us a distance moved of 0.1 meters. If you said that, that's fine. The question is a little bit ambiguous though, because it says calculate where the pivot would need to be moved. If you could say, if you said I'd moved it 0.1 meters from its original position, then that's completely fine. If you wanted to say where it was located on the ruler in terms of its, like the 10 centimeters, 20 centimeters, etc., then if it started at 50 centimeters and then was moved left 0.1 meters, then its actual final position would be at 0.4 meters or 40 centimeters. So either or, if you got that, well done. Thanks for watching. I hope you found that helpful, and I'll see you at the next one.